I just had a quick question.
Yes. How can I help you, Danielle?
I emailed you, I think yesterday or maybe over the weekend,
Mhm.
but you said you moved the test to next week, next Monday and Tuesday, right?
Yes, I did.
So I can't do Monday or Tuesday. Like I don't have any time in my schedule. So is it possible to maybe do it on Wednesday?
So actually, you might have misunderstood a little part of it. So the test that is due, it's actually due on for your class. It's due on Monday afternoon by 11 or Monday evening by 11:59, and it's an online test. You can do it anytime starting now or anytime between now and then.
Oh, okay. That makes more sense. Thank you so much.
You're welcome. Yeah, so I did move everybody just for the record, and since I've got, four or five of you in here now, I did move the first online test, which was supposed to be due today, or actually, yeah, it was supposed to be due yesterday at 11:59 p.m. for class today. I moved it back so it's due one day, 1 week from today at 11:59 p.m. or actually 1 week from yesterday at 11:59 p.m. So that's an online test and it's only on chapters 17 and 18. And then the following week, there's another one that's on the chapters 19 and 20. And that's also an online test. And then our first face-to-face test should be coming around probably very late September or maybe early October. I can't remember, but it's on your syllabus. We're still sticking with that date as best I can tell. So,
Quick question, Professor.
yes.
It says that the online test is due on Sunday, not Monday of next this coming.
That's probably going to be the way the syllabus says the whole time. I'm going to give y'all guys the Monday since your class meets on Tuesday anyways. But it does, in fact, right now, if you look at the test, I know for a fact that it says the 22nd, which should be Monday, but I'm moving it right at this moment to the 23rd.
Yeah. And also it doesn't show that it's available yet either.
Okay, let me make sure that I click on that button. This would be 9/23. So that's the new date is 9/23. And 11:59 p.m. on 9/23. Oops. Okay, for some reason it's getting weird colors here. I do that. All right. All right. So now I've got it listed as yeah, it should be available. Move that to 23. Move that to 23. It says published. And you're looking at OT01, chapter 17 and 18. Is that correct? Is that what you were looking at? Micah, I think that's who it was.
Yeah.
Okay. What happens when you click on it? Oh, I see. Hold on.
It says just not available or hasn't been made available by the instructor yet.
Gotcha. I see why it's listed, but it's in a module that hadn't been published. So I bet you it works now. You might have to back out of that page and then go back and then try it. Hopefully that'll work. don't, I mean, if
It,
you
it
try,
works now. It gives the option to take it now.
okay, cool. So yeah, don't try to take it, of course. But anyways, yeah, evidently that's something new I just learned. I was always worried that if I had something in a module and left it unpublished, that y'all could still access the thing if it was published inside the module that was unpublished. So that just answered that question. Evidently, you can't touch anything while it's in a module that's unpublished, even if the object itself is published. So, all right, well, that's available now. And you're going to see the next online test, which will cover chapters 19 and 20. That will be due a week later. So that'd be September 30th. So any other questions? All right. So probably the most important aspect of chapter 19 that we're doing is really more about what we call calorimetry. So I've already talked to you a little bit about specific heat, and we're going to use that, for instance, to do calculations of how much heat it takes to warm a certain mass of substance up from a certain temperature to another temperature, and so on and so forth. As long as we can find the specific heat for that particular material that that object's made of, that's a no-brainer. So what I'm going to do is I'm going to start with an example very much like one in the book. In fact, I'm probably just going to take the one from the book, which is example 19.4. And it says, if 200 cubic centimeters of T, so let's see. I got another person came in. Hold on a second. I'm going to copy this down and let me go ahead and share my screen first. I was going to do it after, but I decided on the fly to go ahead and do it now. So I've got people coming in. The screen should be sharing now or very soon. So what we're looking at here is if 250.0 cubic centimeters of T at 99.0 degrees Celsius is poured into a 175 gram glass cup initially at, what were they? 22.0 degrees Celsius. What will be the final equilibrium temperature? Now, there's a couple ways you can do this. I'm just going to call this example 1. Okay, there's a couple ways you can do this. I tend to do it one way, and your book is trying to show you both ways or two of the ways. So the way I do it is I normally think, all right, when I have a calorimetry problem, what I'm imagining is ideally I have something called a calorimeter, which is a double-walled container of some sort, the inner wall of which is a container that can be pulled out and weighed so that you know exactly what that inner container is made of so that you can use specific heat for it, and you know its exact temperature so you can use its initial temperature. And you, of course, can weigh it so you know its exact mass. And then that calorimeter is has water in it usually, and then you put something in it and and basically all the heat stays within that inner cup, the water, and the thing that you put in there. And once it all reaches equilibrium, all three of those things are at the same temperature, and the calorimeter has prevented a good fraction, if not very much near 100% of the substances from losing any heat to the surrounding. That's what a calorimeter does. In a lot of cases, the process can happen so quickly that it really doesn't lose too terribly much energy to the environment anyway, so you don't necessarily have to have a calorimeter, and that's what we're doing here. So in this case, we have a 250 cubic centimeters cup of tea, and the tea itself is at 99.0 degrees Celsius, and it's poured into a glass cup. So we know the container is actually made of glass, so that's something we can look up the specific heat of. And that glass is 175 grams, and it's at initial temperature of 22.0 degrees Celsius. And they're asked what's the final temperature of the system. So we can go on the assumption, and your book, for instance, has an example just like this, and it says we can make the assumption that tea is essentially water. That's not a bad estimate until you start talking about sweet tea. So if you start mixing in sweet tea, there's a high probability that the water changes a huge amount from water to tea when you add not only tea, but a appreciable amount of sugar. So in this case, we're just talking about sort of British tea that would come out hot, and it's, basically the tea is almost like a little bit of a it's a very dilute thing. In other words, there's a small mass of tea compared to the mass of water. Therefore, the tea is pretty much irrelevant. So the two ways that I normally talk about this is, one, we treat all the objects that are warmer and giving up heat as one source, and then we treat all the other things that are actually absorbing heat as another object, and we set the heat of those two objects equal to each other. So Q lost equals Q gained is what I would say. Another thing you can do, and your book tries to do both, and just in a lot of examples, it's the sum of the Q's would equal 0. That should be the same thing, because, when one's losing heat, then Q is negative, and when one is gaining heat, Q is positive. So the sum should be 0 if nothing's wasted. My problem with that is I've discovered over the years that not only my students, but me personally, often make careless mistakes worrying about signs and the stress of a test. So by doing it this way, Q lost equals Q gained, I just make sure all the terms are actually positive, and that way I don't have to worry about, is that latent heat of fusion, is that a positive or a negative? Is that latent heat of vaporization, is that a positive or negative? What if I'm going from liquid to solid? Okay, what if I'm going from solid to liquid? All that stuff causes other problems. So I'm going to go with that, and I'm going to use the technique of heat lost equals heat gained. And I'll allow you to just, look at your own book to see the similar examples that they do with the summation of the Q's equals 0. So here's my solution. One, I'm going to assume T is water. 2, I know that when you add heat to a mass M of substance whose specific heat is C, you get a change in temperature delta T given by Q equals MC delta T. So that's what I'm using. I'm also going to use Q lost equals Q gained. Okay, so that's what I use, rather than the summation of the Q's is equal to 0. So in this case, the thing losing heat is the T. So I'm going to say QT equals Q cup. Because all that's going on here is we're pouring 250 cubic centimeters of 99.0 degrees Celsius tea into a 175 gram glass of water, a glass cup. at 22 degrees Celsius. So it's really only two bodies. The actual tea will cool down and the actual glass cup will warm up. So that's the way I'm working this out. With that in mind, I get the mass of the tea, which is, since we know the density of water, rho H2O, is equal to 1 gram per cubic centimeter. Because of that, we know that 250.0 cubic centimeters implies someone has their speaker on. Let me see if I can figure out who it is just to let y'all know. Might be you, Carter, or possibly Danielle or Micah. Nope, Micah's not it. So it's Danielle or Carter have your speaker on. I hear background noise.
It's not me. I can hear it, but it's not me.
No problem. Just letting it's not bothersome yet, but I figured it might get louder or embarrassing or something. So 250 cubic centimeters of tea is going to be basically 250.0 grams of tea. So now I can say 250.0 grams. I'm using the MC delta T formula. I happen to know that the specific heat of water and therefore tea is about 1.00 calories per gram Celsius degree. And I know that the final temperature is going to be lower than the initial temperature. But when I do QT equals Q cup, which is Q loss equals Q gain, I expect all the terms to be positive. So that's just a little reminder. Assume/make each term positive. Okay. So in this case, 99 is the initial temperature and the final temperature is going to be lower. So I want to do 99 minus the final temperature. That way it'll keep it as a positive. So I'm going to say 99.0 degrees Celsius minus T final. And then I'm going to set that equal to the Q gained for the cup. And of course, the mass of the cup is 175 grams. The specific heat of the cup is a little different than water. I'm going to refer back to the table, table 19.1. And table 19.1 tells me that the specific heat of glass is equal to 0.20 calories per gram Celsius degree. I'm using calories because I happen to know a lot of those figures off the top of my head. So that's why I'm using that. I'm going to put 0.20 calories per gram Celsius degree. And then this time, the initial temperature is 22, but the final temperature is going to be larger. So I want the final temperature T to be subtracted from it the initial temperature. So I'm going to do T minus 22.0 degrees Celsius. So that's how we actually calculate the or set up the equation. Now we're just going to multiply through, distribute everything, and then solve for T. Does anybody have any questions so far? Okay, and yes, by the way, you might want to go ahead and chat your first and last name. I see 3 of you have already done it, so at least that way you won't forget, but you can go ahead and do that now. You can also, of course, chat if you have any questions. If your speaker works, though, I'd prefer you to just speak up because there's a good chance I might not even notice the chat. All right, so I'm going to take the 250, I'm going to multiply that by 1. And then I'm going to take that quantity and multiply by 99. So I'm going to say 250 times 1 times 99. And that's 3 sig figs for all of that. And that's all multiplication. So the 3 sig figs should be the answer, the number of sig figs that the answer should have. And that's going to be 24,750. And the units at that point become essentially just calories, because the gram cancels out with a gram, and the degree Celsius sort of cancels out with Celsius degree, so that's good enough. But we sort of use the Celsius degree compared to degree Celsius just as a little helper. So it really does cancel out. It just looks like it doesn't. Since I'm only having 3 sig figs, I'm going to underline the 50 because only the 2, 4, and 7 are significant figures. Now the 250 times the 1 also has to be multiplied by the final temperature term. So that's going to be minus, notice when you multiply 250.0 grams times 1 calorie per gram, I just get calorie per Celsius degree. So this is going to be 250.0. Now, since I multiplied by 1.00, it only has 3 sig figs, so that 0 is no longer significant. And this is going to be calories per Celsius degree times T final. Notice the minus, okay? Similarly, I'm going to take the 175 on the right-hand side and multiply that by 0.2. And that gives me 35. And then I'm going to multiply that by the T. And that would give me 35 calories per Celsius degree times, that's supposed to be T final. I just didn't write a final subscript on it last time. So now I'm putting the subscript on there. Now I also have to multiply the 35 times the negative 22. And of course, that's 3 sig figs. Actually, by the way, since I multiplied that 175 by 0.20, it no longer has 3 sig figs. It only has 2. So I'm going to have to make this 35.0 with a line under it. And when I multiply the 35 times negative 22, I'm going to get negative 770 calories is all that's left now. And in fact, since I only have 2 sig figs, that 0 on the end is not a significant figure. So I'm going to add 770 calories to both sides. And I am going to, actually, I don't want to do it that way. I should have done it the other way. So let me scratch that technique. I'm going to pull all the calories to the other side by subtracting 24,750 calories. Oh, okay. No, I was right the first time. I just realized that the 250, which is bigger, is already negative. So the when I pull the 35 over there, that's going to become a negative in front of the temperature. And when I pull this over to the other side, then it'd become a positive. So I'm okay with adding the 770 to both sides. So let's do plus 770 calories plus 770 calories, and we'll say 24,750 plus 770 gives me 25,520. But now we see that the 2 and the 0 are not sig figs because the 5 wasn't a sig fig beforehand. So that's taking care of that. Now what I'm going to do is add 250 to both sides. And I'm specifically adding 250 calories per Celsius degree T final to both sides. Okay. So on the right-hand side, I am now going to have 250 plus 35, which should be 285.0. Of course, the sig fig that we have is in the ones place in both numbers, so we can actually carry this out to the ones place, and I have 3 sig figs left over here. and it's multiplied by calories per Celsius degree T final. So now all I have to do is divide by 285.0 and do that to both sides. And in so doing, that'll allow me to solve for the final temperature. So I'm going to divide both sides by 285.0 calories per Celsius degree. Okay. And hopefully that should do it. So I'm going to take the 25520 and divide it by 285. And I get 3 sig figs divided by 3 sig figs gives me, gives me 89.0 degrees Celsius is equal to T final. Anyone have any questions on that? So that's what a calorimetry problem is. Like I said, I could have worked it the other way, and just to give you an idea of what that looks like, I'll go ahead and show it to you. And this also give you more time to think about whether you have any questions. So another way we could have done is solution. Whoa, Nelly. In this case, it's not really hard to do it this way, but the summation of the Q is equal to 0 is the formula we're going to use. We're also using the other formulas that I had. So we're going to use Q equals MC delta T. We're also going to use that T is water. And we're also going to use the fact that the density of water is equal to 1 gram per cubic centimeter. And we're also going to make use of the fact that the specific heat of glass is 0.20 calories per gram Celsius degree. And of course, we already know that the specific heat of water is 1.00 calories per gram Celsius degree. So in this case, what I do is I just write down all the things, but in this case, I have to be very strict about delta T. So what I'm going to do is say the 250 cubic centimeters of T is the same as 250.0 grams of water times 1.00 calories per gram Celsius degree. Now I have to do T final minus T initial. The T final is what I'm solving for. So that'd be T final minus 99.0 degrees Celsius. Now plus, now notice that T final is actually going to be what we expect it to be is 89. So when I subtract 89 minus 99, I'm going to get a negative number. Which is good because one term has to be negative if the sum of the two terms adds up to give you 0. Now the other term is for the glass, and the glass has a mass of 175 grams. It has a specific heat of 0.20 calories per gram Celsius degree. And then the final temperature is T final. And the initial temperature is 22.0 degrees Celsius. And then all that equals 0. So that's the way you would set it up if you wanted to do the sum of the Q's is equal to 0. But notice I had to be very strict and write T final minus T initial in the in place of delta T, as opposed to just searching for which one had to be the higher temperature and the lower temperature. But if you solve this, it should give you the exact same 89.0 answer. Anybody have any questions on that? Okay, so let's try another calorimetry problem. I'm going to call this example 2. I did not want to write it in that color. So here's example 2. Whoa, Nelly. You wish to discover the specific heat of a metal you throw, I'll put that in quotation marks. I'm using rough language here. You're not really going to throw it necessarily because that could make a bunch of stuff splash out and lose some of the stuff that you need. So you throw a 0.215 kilogram sample of the metal at 550.0 degrees Celsius into 0. Actually, let's do it this way. Let's say, yeah, I'll do it that way. That's fine. Into 0.500 kilograms of water at 12.0 degrees Celsius. The water is in an aluminum cup whose mass is 0.200 kilograms, and it is also at 12.0 degrees Celsius. If the final equilibrium temperature is 30.2 degrees Celsius, what is C? Okay, so that's the specific heat we want to know, the specific heat of the metal. I'm just going to call it lowercase c. Our solution is going to involve Q lost equals Q gained. It's going to involve Q is equal to MC delta T. It's going to involve C of water equals 4.186 kilojoules per kilogram Celsius degree. It's also going to involve the specific heat of aluminum, which I'm going to quickly look up in kilograms or kilojoules per kilogram. I am going to say that this is 0.900 kilojoules per kilogram, and and do I want water to be the same way? I got to double check my water since I'm using that. Ah, gotcha. Then that works. Okay. Let me fix that. I was misremembering my specific heat for water. If I use just plain joules instead of kilojoules, then it's 4,186 joules per kilogram Celsius degree. And then the specific heat of aluminum is 900 joules per kilogram Celsius degree. So I've got water, I've got aluminum, what should be it. All right. So Q lost. What's losing heat here is the metal sample. Okay. So I'm going to say Q metal is equal to Q water plus Q aluminum. In other words, aluminum is taking on heat to be heated up. A water is taking on heat to be heated up. So those two are on the right-hand side. And now I just have to write everything out. So the mass of the metal was 0.215 kilograms. The specific heat is what we're looking for. So I'm just going to write that as C. And the change in temperature is obviously going to decrease in temperature. So the final temperature would actually be lower. So that means I'm going to do it in the opposite order so I can keep the signs positive. It's going to be 550.0 degrees Celsius minus the final temperature, which we actually know. That final temperature is 30.2 degrees Celsius. And that's the entirety of the heat loss for the metal. For the water is going to have a mass of 0.5 kilograms times the specific heat of water, which is 4,186 joules per kilogram Celsius degree. And the water temperature is going to change from 12 degrees Celsius to 30.2. Again, I need to do a positive number, so I'm going to say 30.2 degrees Celsius minus 12.0 degrees Celsius. And now I also have the term for the aluminum cup, which has a mass of 0.200 kilograms. And that has a specific heat of 900 joules. I'm going to assume that's 3 sig figs, by the way, joules per kilogram Celsius degree. And this one's also going from 12 degrees Celsius to 30.2 degrees Celsius. Okay. So I've now got all the terms accounted for. I'm going to go ahead and do the math on all of them that I can do it for. So I'm going to take the 0.215 and multiply that by 5. Actually, before I do that, let's take the 550 minus 30.2. And we see that we have sig figs all the way down to the 10th place. So this quantity right here is going to be 519.8 Celsius degrees. And this quantity right here is going to be 30.2 minus 12. And again, they are good to 1 decimal place. So this gives me 18.2 Celsius degrees, as does this one. Okay. So now I can use that. I can take that 519.8 and multiply that by 0.215. And that's going to give me kilograms times degrees Celsius. And the answer is nearly the answer is 111.757 kilogram Celsius degrees times C. And of course, we only had 3 sig figs when we did that multiplication, because the 215 is 3 sig figs. So the 7, the 5, and the 7 are not sig figs. The 0.5 is on the other side of the equal is going to be multiplied by 4,186, and that has 3 sig figs. So 0.5 times 4186 times 18.2. All of those have at least 3 sig figs. So that answers 38,092.6. But it only has 3 sig figs, so that means the 9, the 2, and the 0.6 are actually not significant figures. So only the 38 and the 0 are sig figs. Of course, when you multiplied all that, you got joules out. And then the next term is the 0.2. Whoa. So 0.2 times 900 times 18.2. Again, the number with the least sig figs still had 3 sig figs. This answer came out to 3,276. And 3 sig figs means only the 3, the 2, and the 7 are significant. So I set that there, and that comes out to be joules by the units. So now all I have to do is add those quantities. 3,276 plus 3,8092.757 gives me 41,368.757 joules for the right-hand side. Of course, we already know that these digits are not sig figs. I didn't really have to carry them, but I think it's probably a little clearer to you guys when you see exactly all the digits that came out. You can know exactly where I got everything. And then I have 111.757 kilograms Celsius degrees times C. So all I have to do to find C is divide both sides by 111.757 kilograms Celsius degree. Again, the 7, the 5, and the 7 are not sig figs. And whatever you do to one side, of course, you got to do to the other. So this is 111.757 kilograms Celsius degrees. And you see the right-hand side is going to come out in units of joules per kilogram Celsius degree. And of course, that's going to give us C is equal to, I'm going to take the 41,368 and divide it by 111.757. Again, didn't need to carry nearly that many sig figs. 1 extra sig fig would be sufficient. I usually carry 2. But when I carry out this division, I get 370.2. And that's joules per kilogram Celsius degree. And that is the specific heat of the unknown metal. Okay. I should mention that each of the numbers that I divided had 3 sig figs, so that 2 is an extra digit. But I did underline it, so that specifies everyone. I know one thing I do on my videos is I try to trace out the sig figs. That's mainly so you can get used to doing the sig fig calculations when you're doing your online homework system. That being said, I've worked with a lot of online homework systems, and all of them are riddled with errors. But in an attempt to make sure that these people would stop making those errors, I try to show the proper way so that maybe you will someday become a student that works on those pages and corrects the significant digits issues. So anyways, does anyone have any questions on that one? To give you a little bit of insight, Copper has a specific heat of 390 joules per kilogram Celsius degree. So this metal seems pretty close to that of copper. Glass has 840, aluminum has 900, lead has 130, silver has 230, mercury has 140. None of those are anywhere close. So it's kind of close to copper. I would suspect if it's an unknown metal, it might have copper in it. But it could be, something that is equidistant above 370 and something that's equidistant below 370 and they're like in a mixture of half to half or something so that it would come up with 370. But either way, doesn't matter too terribly much. It's just a hypothetical we made up. So does anybody have any questions on how these calorimetry problems are solved? Okay, your book did a problem very much like this, and in theirs their numbers were all different, but it was more or less the same problem, and they ultimately determined that specific heat was 497 joules per kilogram Celsius degrees. So you've got more examples to look at if need be. Now, the other thing, your book takes the time in section 19-4-1 to talk about a bomb calorimeter. I happen to know, for instance, that Virginia Tech has a bomb calorimeter. And what that is you can send them some kind of, let's say, dessert, or like my friend from high school, he actually makes hot sauce in Virginia Beach, actually has a homemade hot sauce that he makes. Actually, he's got several of them. They're called Speedies. So Speedy 44, Speedy 45, Speedy 46. He also has like a Speedy's Bloody Mary mix, all sorts of stuff like that. But when you do that, there's certain things that have to be done. And for instance, you have to have a nutrition label that tells you your ingredients and how much sodium and all that stuff. Well, labs have to do that, and he sends his stuff to Virginia Tech. And I know for a fact, because of that, that Virginia Tech has a bomb calorimeter. So if you make a food item like a Twinkie or a cake or hot sauce or something like that, you've ultimately got to figure out how many calories are in it. And what they use for that is called a bomb calorimeter, where basically it's a calorimeter, but you actually more or less burn the food and then find out how much energy comes out of it in either joules or in calories. And then that has to be used to be printed on the label. So that's why your book does talk about the bomb calorimeter. So I just like to let you know that, and also let you know in case you ever happen to go into business and you want to sell products to the public, you're going to have someone to measure the caloric value of the quantity of the stuff, and Virginia Tech, of course, does that. And he said it, at least they did it for free for him. That might have been a first-time thing, maybe subsequent versions they charged him for, I'm not sure, but either way, he said they didn't charge him anything, so that's kind of neat. He's on Virginia Beach Boulevard. There's a shop called Speedy Hot Sauce or something like that you can check out if you want. His name's Jimmy Miller, so check him out. His hot sauce is delicious, by the way. All right, so there's another thing that can happen when you add heat to a system. Obviously, you know that heat can be added to a system to cause it to change temperature, and that occurs according to the equation Q, the heat, is equal to M times C times delta T. But it turns out there's a flat amount of energy that you have to put in once you get, let's say, ice up to 0 degrees Celsius. Then you've done all the changing of temperature necessary to melt the ice, but you still need some more energy to break the nuclear bond, or excuse me, to break the molecular bonds between the individual molecules of ice. That is called the latent heat of fusion. Well, it sort of is. Fusion, I would argue, is in going from a liquid to a solid, and then vaporization would be going from a liquid to a gas. So one has to be positive in terms of heat of fusion. You actually have to put a positive amount of energy to break up those bonds. And if you're going from liquid to a solid, you'd actually have to have a negative amount of heat. And the same thing happens with heat of vaporization. It would take a positive amount of heat to melt the ice, or excuse me, to turn the liquid into a gas, whereas taking it and bringing it from a gas into a solid would actually absorb some energy. So, or excuse me, expel some energy. All right. So what I'm going to do is walk you through a process of what would happen, for instance, if you had 1 kilogram of water. So I am going to draw a coordinate system like this. This is going to be temperature in degrees Celsius. And then on this horizontal axis, actually, I don't think I want the horizontal axis there. I'm going to make the horizontal axis right here. This is measured as actual heat. So this is Q, and it's measured in kilocalories. Okay. So if I start off with water, let's say at -40, this is going to be 1.0 kilogram of H2O. Okay. I'm going to start off at a temperature of -40. And then I'm going to go, of course, through -20 and then 0. Okay. Now, what's going to happen when I do this is the water is actually going to change temperature from -40 to 0. And that's going to take what we might call 0 calories or kcals to 20 kcals. And then what's going to happen, and this is why, for instance, we boil water when we're cooking things a lot of times. It turns out when you go to change the state of a substance, you bring it to the critical temperature at which it changes state. For instance, the melting point for ice or for anything for that matter, or the boiling point is another one. In this case, we are talking about water and ice and stuff. But when you bring it to that temperature, then all of the water or whatever you have stays that fixed temperature until the entire latent heat has been added, and only then does the temperature change. So, for instance, if you needed to, let's say, get the innermost piece of ham on a really big chunk of ham, so like a 4-pound ham hock, for instance, or a 6-pound ham hock or something, the thickest part of that meat is actually, quite thick, and it's really hard, especially if it, for instance, was frozen. It'd be very hard to make sure you get the temperature high enough so that you don't get some kind of, foodborne disease from eating raw ham. So it turns out if you put it in boiling water is at 100 degrees Celsius, and the temperature at which those waterborne or foodborne pathogens dies might be on the order of, let's say, 160 or 170 degrees Fahrenheit, which is, still quite a bit under 100 degrees Celsius. So you can actually stick the whole ham hock in the water at 100 degrees Celsius while it's boiling, and eventually the water, the pot, and the ham, all the way to the innermost piece, will all reach equilibrium at 100 degrees Celsius. You don't, of course, want it to go that far. You just want to make sure the inner part gets to like 165 Fahrenheit. So that's one of the reasons you could do it, is because it turns out that substances reach their critical melting point or boiling point and then stay that temperature until they're completely melted or boiled. So now that we've got the water up to 0 degrees Celsius, it's going to, in fact, stay at 0 degrees Celsius until it reaches or until you put in an additional 79.7 kilocalories is really what you got to put in. So I'm going to say this would be about to 40, 60, 80, and then about 100. So this would be right at 100 kilocalories. In principle, though, it's actually just 79.7 kcals. Okay. But that's the heat of fusion for turning water from a solid to a liquid. Okay. Now that we've got it up to 0 degrees Celsius and we've put in enough heat to actually break the bond so it can become liquid, now we have liquid water, and the specific heat of that is 1 calorie per gram Celsius degree, which would be 1 kilocalorie here. So all we have to do now is actually add more heat to heat it up. So in this case, I'm going to go from 0 up to 100. So I'm going to call this, putting in red again, this is going to be 20 degrees Celsius, 40, 60, 80, and then 100. And what we expect to happen is that this is going to take a little bit of distance to, in other words, a little bit of energy to bring that kilogram of water from 0 degrees Celsius to 100 degrees Celsius. So you can imagine, since the specific heat of water is 1 calorie per gram or 1 kilocalorie per kilogram, then you'd expect it to be, for 1 kilogram, it would be basically 1,000 kilocalories to crank it up. I'm going to go with what your book is using, and I'm just going to draw the line right here to there. And that's the phase where the water is just changing temperature. Okay. And your book is arguing that that is, in fact, another 100 calories. So I'm going to draw a dashed line. That's going to bring us up to 200. What you can say is Q is equal to 1.00 times 10 to the third grams. That's what a kilogram is, times 1.00 calories per gram Celsius degree, times 100.0 degrees Celsius minus 0.0 degrees Celsius. And you can see that this is going to be 1,000 times 1 times 100. And that gives you 100,000. Calories. And of course, that's 100 kilocalories. So that's exactly right. This is going to take 100 kcal in here. And now I've brought the water up, which before was ice. Let's write it here this way. I think I'll use purple. So I'm going to say the ice is all there. And then when I get to this phase, it's going to be all water. So I'm going to say water. Like that. Okay. But at that point, it's going to reach 100 degrees Celsius. And just like it did when it went from ice to liquid, it's going to maintain that temperature for a long period of time. And in fact, it's going to be until you put in another 539 kilocalories. So what I can do is I can say, it looks like I'm using 3 as 100, and I need to go up to 740. So I'll try to make it the scale. Let's check it out. So this would be 300, 400, 500, 600, 700, And then 40 would be, well, 100 is 3, so 33 would be that. So it'd be a little bit more than that. So that'd be about 740 right there. So that doesn't work too badly. So I'm going to call this part right here 740 kilocalories. Okay, that corresponds to just a little bit past that gray line. What's going to happen now is all during that time, the water is going to maintain a temperature of 100 degrees Celsius. And then it's going to change state. And what actually had to happen here was we had to put in enough heat to cover the heat of vaporization. And in this case, like I said, it's 539 kilocalories. Okay. But all that time, it's still water. And then once you get to that, then it's steam and it starts to climb more. So at this point, it becomes gas. And we might say that it would look, say, something like this color. Whoa, Nelly. So what I'm showing you is these little quantities here are called latent heat. And you can think of it as the heat required to break molecular bonds. And the equation that we use for that is we've already used, for instance, Q equals MC delta T. That's for the slope areas. But for the flat areas, it's Q is just equal to M times L. And L can be latent heat of fusion, latent heat of vaporization. And then anybody know what CO2 would do? It wouldn't be fusion, it wouldn't be vaporization. Anybody know what solid CO2 does?
Would it be sublimation?
Exactly, sublimation. Yep. So those are your quantities, but you can see how the formula works. It's just Q equals M times L. So you just need to look up the heat of fusion. So for instance, when I look up the heat of fusion of water, it says in kilojoules per, well, let's do kilocalories. Kilocalories per kilogram, the latent heat of fusion for water is 79.7, whereas the heat of vaporization is 539. So what I'm going to say now is this quantity is L fusion for H2O, and this quantity is L vaporization for H2O. And table 19.2 has those values. The other table we had the specific heats. So I will remind you here, table 19-1 has specific heats. Okay, so that's where I'm getting those. And I've got the heat of fusion, the heat of vaporization, the heat of sublimation, all that kind of stuff. That will be in table 19.2 in your textbook. And they not only put them in your textbook so that you'll have examples of how big the numbers are, but also so that you can use them to solve physics problems. Okay. So let's look at a typical example. Let's say, for instance, this will be example 3. In example 3, I'm going to ask how much energy that's a Y. Let me make that Y a little clearer. I don't like it. how much energy has to be removed from 2.50 kilograms of water at 22.5 degrees Celsius to make ice at negative 15.0 degrees Celsius. So that's the question we're going to ask ourselves. And now we're going to solve it. Does everybody understand what we're doing here? All right, so let's do solution. What we know is we have the formula for changing the heat of the temperature of something. That formula is Q equals MC delta T. We have the formula for adding heat to change the state of something. That is Q is equal to M times L. We know that the specific heat of liquid water is CH2O, and I'll put a L on it just to remind us that it's liquid, because it turns out that the specific heat of water is different than the specific heat of ice, and that's different than the specific heat of steam, even though they're all quote unquote water. So the specific heat of water, since we're giving kilograms, I'm going to go ahead and quote this in kilojoules per kilogram, and I'm going to go pull it from the table real quick. Looks like it's in the, there you go. So the specific heat of water, liquid water that is 4186. And that's joules per kilogram Celsius degree. The heat of fusion, which is what we need for water. Actually, I'm also going to need the specific heat of water in the solid state. So the specific heat of water in the solid state is going to be, and this is technically for -5 degrees Celsius. Remember, when you're actually doing these things, you need to find the most precise values of specific heat you can for as many temperatures as you can between the initial temperature and the final temperature, and then attack it piecewise so that you get the most accurate result. I'm only given one specific value of specific heat, so I'm pretending like that covers the whole range when it doesn't necessarily cover the whole range. So in this case, I'm going to say that the specific heat of ice, instead of being 1 calorie per gram, it's actually half of a calorie per gram. So in joules per kilogram degrees Celsius, it turns out to be about 2100 joules per kilogram Celsius degree. That's the specific heat of ice. The one for steam is 2010. So that would be the one for gas. So just for the record, I'll put it on here so you'll know specific heat water for the gas is equal to 2010 joules per kilogram Celsius degree, but we clearly don't need that. Okay. And oh yeah, we also need the latent heat of fusion. So I'm going to go get that as well. The heat of fusion for ice, we already found, was like 79.7. I'm going to double check that. That's kilocalories, and I actually want it in joules. So yes, 79.7 is right. But what I'm going to do is say the latent heat of fusion for water is 333, and that's kilojoules per kilogram. Okay, it's 79.7 in kilocalories per kilogram, or 79.7 calories per gram. Either of those are acceptable. So now that I have all that information, I can go ahead and calculate the heat change that's necessary. So I'm going to say Q required is equal to, now we know the mass of the water is 2.50 kilograms. And notice, unlike the volume, the mass is never going to change. So you don't have to worry about that since they gave us masses. But if they had given us volumes, I couldn't just use the 1 gram per cubic centimeter because it has a different density for the ice than it does for the water. So here's, as a liquid, we're going to have 2.50 kilograms of water that has a specific heat of 4,186 joules per kilogram Celsius degree. And I have to bring this temperature from 22.5 to 0 to make it freeze. So the final temperature is going to be 0.0 degrees Celsius minus the initial temperature, which is 22.5 degrees Celsius. And that's just to bring the water from 22.5 to 0. Once it's at 0, then I've got to change the state, and that means I've got to address the latent heat of fusion. So I'm going to write 2.50 kilograms times 333 times 10 to the third joules per kilogram. Notice how I put 10 to the third there, so everything comes out in joules. And that gets me to an actual solid chunk of ice, but at 0 degrees Celsius. So now I have to go back and add some, take away some more heat. This time, by the way, I should make that negative since everything's coming out negative. So let me put a negative sign in there like that. Now back to the other part. 2.50 kilograms is the mass of the now ice. The specific heat of the now ice instead of liquid water is now 2100, and that's joules per kilogram Celsius degree. And this temperature, the final temperature, is going to be negative 15.0 degrees Celsius minus 0.0 degrees Celsius. So we have to take out heat. That's why I put that negative in there for heat of fusion. That's also the reason why I tend to use Q loss equals Q gain, because it's hard to remember whether the latent heat of fusion and going from liquid to a solid is negative or positive, or when you go the other way, is it negative or positive? So that actually remedies that. But now you can see how it has to be. Now let's go ahead and compute each term. So I'm going to take 2.5 times 4186 times 22.5, because it's 0 minus 22.5, and times negative 1 just to make sure it's negative. So this gives me negative. Notice I only had 3 sig figs, so I'm going to carry 5. So this will be 2.35. There's 3. 46 times 10 to the 5th. And the answer comes out in joules. Okay, so that's just the first term. And then I'll put a minus for the second term. That's 2.50 times 333 times 10 to the 3 times negative 1 again. That gives me a really big number, 832,500. So this is going to be negative 8.32. This one also had only 3 sig figs, so I'm going to carry 2 more. So I'll put a 5 and a 0 after it, and I'm going to say that's times 10 to the 1, 2, 3, 4, 5. Ooh, was that last one also 5? 1, 2, 3, 4. Yeah, it was 5 as well. Joules. And now I've got to take the last term, which is 2.50 times This time I'm going to write the negative in the 2100 just to keep it negative. 2100 times 15. So in other words, I made it negative just by making the 2100 negative, and the negative 15 minus 0 just gives you the negative 15. So I ultimately get the right answer just by multiplying 2.5 times 2100 times negative 15, and that gives me negative 7.8750 times 10 to the 4 in this case, joules. So now I can add all these quantities. I'm going to say the negative 78750 minus 832,500 minus 235,462.5. In other words, I'm carrying all the digits now. And that gives me negative 1.14. I'll keep one extra sig fig this time. That's going to be a 7 times 10 to the 6 joules. So that should be how much heat we have to remove. And the fact that it's negative tells us that we have to remove that heat. Anybody have any questions on that one? No questions? Your book did a very similar problem. And it got like 660 kilojoules, but the numbers were quite a bit different. But it's still in the same ballpark. I'm just barely over 1 million, and 660 kilojoules is just barely under, or just barely under 1 million. So that seems fairly reasonable. They did use water. Oh, okay, but they used a lot smaller quantity. Their quantity was 1.5 kilograms, and the initial temperature was 20, not 22. And their final temperature was negative 12, not negative 15. So that makes sense that mine should be markedly larger, even though it's both negative in all those quantities. So anybody have any questions on that? All right, so that's example 3. That gives you a pretty good estimate of how to do these problems. Let me look a little further in the section and see what else is to be covered in this chapter. We're in chapter 19, the evaporation, kinetic theory of latent heats, first law of thermodynamics. Yes, all that stuff's important, and that's what we're going to do next time. So I will start in the section on evaporation. There is an example that I didn't solve. Anyone like it? So I definitely recommend you reading up that. I may or may not solve it next time. I probably won't, because I think it's straightforward enough where you can figure it out yourself. But I'm going to put it in here and just say, whoa, Nelly. Make sure you all read and understand example 19-7 from your text. Okay. In other words, you really should be reading the chapter. The bare minimum of quote unquote reading the chapter is at least going through and thoroughly reading each example, making sure you can understand why they did what they did, making sure you can fill in the gaps. Like if they get from one line to another and you don't know how they got from that one line to the other, you need to figure that out. Also, in the paragraphs, anything you see italicized or boldface, you probably need to write down and commit it to memory or think about it a lot, because chances are they were telling you that for a good reason. So as a bare minimum, I'd say do that kind of reading for the rest of chapter 19. And next time we're going to finish off chapter 19. I'm not going to do the derivations from chapter 19. This is a really long chapter. We're going to start off with evaporation, kinetic theory of latent heats, first law of thermodynamics. And then we're going to talk about thermodynamic processes like isothermal, adiabatic, isobaric, isovolumetric, and stuff like that, free expansions. And I'm just going to roll with the equations and use them to solve the problems. If you want to see the actual derivations and understand them, you can look in my YouTube channel for lectures that I've done on chapter 19, and you'll see me deriving these results. You can also, of course, read the book, which does the derivation, but it's going to go through all those different processes, and then we're going to solve problems, and then we're going to go to actual heat transfer. So we're going to talk about the ways you can transfer heat from one object to another, those being conduction, where two things are physically in contact with each other, convection, which uses like an intermediary fluid, and then radiation. And we don't do much with convection, but you should understand how it works. I'll give you a hint. That's more or less how our air dryer, or excuse me, our some of the new cooking things work. If you have a hot air fryer, that is a type of convection oven. And the fact that they can do things so quick is because convection is even more efficient than just conduction or just radiation. In fact, convection sort of allows you to involve, in that case, basically all three ways. But there's really only equations for conduction and for radiation, and we're going to learn those equations as well. I hope I can finish chapter 19 next time, but I'm not positive I can. It's now 6:38, so we've finished for tonight. Make sure you put in your first and last name in the chat, so I have you down as being here, and you guys are free to go. Don't forget, you do have a online test that is due Monday at 11:59 p.m. covering chapters 17 and 18. I'll wait for the last person to leave in case anyone has any questions.
All right, have a good night.
You too. That's it. Everybody's gone already. Man, they fast. All right. See you, folks. Bye-bye.